Charged particles in magnetic fields. When a particle carrying a charge q travels at right angles through a magnetic field of flux density B with a velocity v, it experiences a force F, where F is given by BQV. The force is perpendicular to both the magnetic field and the velocity, and its direction can be found from Fleming's left-hand rule. To use Fleming's left-hand rule, you must use your left hand, and you point your first finger in the direction of the magnetic field. Your second finger must point in the direction of the conventional current. That is the way positive charges would be flowing. So if electrons are flowing in this direction, the current is actually in this direction. The thumb then points in the direction where there would be motion, the direction of the force, or thrust you could think of it as. If the direction of motion of the charge is not perpendicular to the field, so for instance here we have a magnetic field acting vertically downwards, and the velocity of the charge is at an angle theta to the magnetic field, well, the component of the velocity that is perpendicular to the field will be given by v sine theta. And so now the force is equal to BQV sine theta. Here we have a charge q moving to the right with a velocity v in a uniform magnetic field directed into the screen. So using Fleming's left-hand rule, if you point your first finger towards the screen for the field, this is a positive charge, and so this is actually the direction of current, so point your second finger to the right. Your thumb for the thrust will now be pointing upwards, showing the direction of the force on the charge. This will cause the charge to move in a curved path to maybe here. Now the force will be towards the left like this, with the velocity in this direction. So the charge will continue on a curved path to here, and then to here maybe, and round to here. So the charge will map out a circle, something like this, of radius r. So the force due to the charged particle moving through the magnetic field is providing the centripetal force needed to produce the circular motion. And so we can say that BQV, the force due to the charge moving through the magnetic field, is providing the centripetal force mv squared over r. So the radius of the circle is given by mv over bq. Here we have what is called a fine beam tube. This allows us to find the charge to mass ratio of the electron. It consists of a tube of low pressure gas, a vertical electron gun, meaning it can fire electrons up or down from here, and a pair of Helmholtz coils. These are coils which produce a uniform magnetic field, which I'll say is going to go into the screen. The electrons then will follow a circular path, something like this. We can confirm that using the arrow I've positioned here and Fleming's left-hand rule. If the field is into the screen, point your first finger of your left hand towards the screen. If the electrons here are moving to the right, the current is to the left. So if you point your second finger to the left, your thumb for the thrust is pointing downwards towards the centre of the circle. Of course we can't actually see the beam of electrons, but the electron beam does cause the gas to glow, and we can see this glow. This allows us to measure the radius of the circle. Now to run through how this arrangement allows us to find the charge to mass ratio of the electron. Well, from the electron gun, we know that the electrical energy gained from the charge on the electron multiplied by the potential difference it goes through is equal to the kinetic energy of the electrons leaving the electron gun. We can rearrange this to find that the speed of the electron is equal to root 2 eV over m, being very careful here that lowercase v is the speed of the electrons and the uppercase V the potential difference. Also, we've just shown that the force on the charge moving through the magnetic field is equal to the centripetal force. If we rearrange this equation for V, we found that V is equal to BER over m, where B is the magnetic flux density, E the charge on the electron, R the radius of the circle, and m the mass of the electron. What we can do now is bring these two terms together to get this expression. Then, if we square both sides, we get this. And we can rearrange to the charge to mass ratio of the electron being given by 2 times the potential difference of the electron gun over the magnetic flux density B squared and the radius of the circle of the electrons squared. So these are all measurable quantities, allowing the charge to mass ratio of the electron to be calculated. This value was found in 1897, albeit by a different method, by J.J. Thomson. 12 years before, Millikan found the charge of the electron E in 1909.